Along this lecture, we'll answer on two questions. In the first question, we'll find out the area of this semicircle that is inside quarter circle AOB. And in the second question, we'll find out the area of this pin shape that is inside rectangle ABCD. So let's start with the first question. So in the drawing, we have quarter circle AOB. You know that side AO of this quarter circle AOB equals to 5 units since left. That is to say, the radius of this quarter circle is equal to 5 units. And inside this quarter circle AOB, we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, we will define the center of this semicircle. This point is point C. Likewise, we define the touching point between this quarter circle and this semicircle. This point is point F. And we define the touching point of the semicircle with the quarter circle. This point is point G. Likewise, we define the point of tendency of tangent AO in this semicircle. This point is point H. And finally, we define the point of tendency of tangent BO with this semicircle. This point is point L. In addition, we will define the radius of this semicircle as x. Therefore, CF is the radius of this semicircle is equal to x according to our definition, and CG is also the radius of this semicircle that is equal to x. In the next step, we will join point C and L together by straight line. CL is of course the radius of this semicircle is equal to x according to our definition. Likewise, we will join point C and H together by straight line. CH is of course also the radius of this semicircle is equal to x. So here we can implement rule 1 because we have the radius CL that is equal to x. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, according to the same rule, rule 1, we have the radius CL that is equal to x. The radius CL is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we actually can do the quadrangle C L O H. Quadrangle C H O L. So inside quadrangle C H O L, inside quadrangle C H O L, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this four-piece angle must be equal to 90 degrees in its size. So inside quadrilateral C, H, or L, we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be a tesseract if not a square. So we relate to quadrilateral C, H, or L as a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle C, H, or L, side CH must be equal to the opposite side OL, but CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the sum rectangle CHOL, side CL must be equal to the opposite side OH, but CL is x, therefore OH must be also equal to x. So if we found out that quadrilateral CHOL is not a rectangle but a square, we are because of the fact that all of its sides are equal to each other. Each side of this square equals to x. In the next step, we join points O and C together by a straight line. By joining points O and C, if we can do it, the right and associated triangle CLO. So in the next step, I'll copy the right and associated triangle CLO in a new page and we'll implement the Pythagoras theorem in this right triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a progression for Pythagoras theorem. So really, this is the right and associated triangle CLO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO squared, that is the square of the hypotenuse, equals to CL squared plus LO squared. So right now, CO squared, that is the square of the hypotenuse, equals to CL squared plus LO squared. The hypotenuse CO is the missing side, so we leave it as it is. So CO squared equals to CL squared. CL is x, therefore CL squared is x squared plus LO squared. LO is x, therefore LO squared is x squared. So in total, if we found out that CO squared equals to x squared plus x squared is 2x squared. So CO squared equals to 2x squared. Here we take out of this equation and finally we get that x inside CO is equals to the square root of 2 times x units inside. So this is x inside CO is equals to the square root of 2 times x units. So we know that point O is the center of the quarter circle. So for the center of the quarter circle, that is point O, we have an segment OC that bisects chord FG. That is to say, line segment OC divides chord FG into two halves. Each half equals to x. So CF equals to x and CG equals to x. And whenever you have a line segment that is drawn from the center of the circle and bisect the chord, you can implement all seven. So if it goes to all seven, according to all seven, if a line segment that is drawn from the center of the circle bisect the chord, then that line segment will be also perpendicular to the chord. So in the drawing we have a circle, and this is point O, that is the center of this circle. From this point O, we have here line segment OM that bisects chord AB. That is to say, line segment OM divides chord AB into two halves. MA equals to MB. So, and therefore, according to this rule 7, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord FG. So all the requirements for rule 7 are satisfied, and therefore we can implement here rule 7. According to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 7. We know that the radius of the quarter circle equals to 5 equals AO equals to 5. In the next step, we join points O and F together by straight line. So what is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and ends at point F, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore OF is the radius of this, therefore OF equals to 5. Is the radius of the quarter circle, is equals to 5. So in the next step, I copy this right green triangle CFO in a new page, and we implement the Pythagoras theorem on this right triangle CFO. Here by PT is the evolution of Pythagoras theorem. So actually, this is the right angle triangle CFO that are going through the original drawing according to the Pythagoras theorem. This right angle CFO, FO squared, that is the square of the hypotenuse, equals to FC squared plus CO squared. Again, FO squared equals to FC squared plus CO squared. So I'll write it down. FO squared, that is the square of the hypotenuse, equals to FC squared plus CO squared. FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to FC squared. FC is x, therefore FC squared is x squared plus CO squared. CO is equal to 2 times x, therefore CO squared is equal to 2 times x squared, that is 2x squared. Equation of Sheffield, the 25 equals to x squared plus 2x squared, x squared plus 2x squared, that is 3x squared. So 25 equals to 3x squared. Here we divide this equation by 3 and finding that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of the semicircle? We know that the radius of this semicircle is x, therefore the area of the semicircle must be equal to pi x squared over 2. So write it down. The area of the semicircle, that is the area that we are looking for in this question, must be equal to pi x squared over 2. So it is pi over 2 times x squared, and x squared is 25 over 3, so we substitute x squared in this equation by 25 over 3, and finally we get that the area of the semicircle equals to, here in the numerator we have 25 pi over 2 times 3, that is 6. So in total we found out that the area of this semicircle equals to either 25 pi over 6 square units, so in terms of numbers, this equals to 13.09 square units. So we'll finish with the first question. In the next step, I present you the second question and we will solve it. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units inside. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle BCP. And our mission is to find out the area of this green shape. So first of all, we will define the radius of this quarter circle as x. And BC is the radius of the quarter circle, and it is equal to x according to our definition. We know that all the angles inside the rectangle are right angles, and therefore this angle ADC is a right angle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be equal to 5 units inside. So write it down. this C equals to 5 units in its length. According to the sum rule, first of all, we define the center of this semicircle. This point is point O. According to the sum rule that said that the opposite sides of a rectangle are equal to each other, we get that side BC must be equal to the opposite side AD, but BC is x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of the semicircle. So we know that the diameter of this semicircle is equal to x units in its length. If the diameter is x, the radius must be equal to half of it. The radius must be equal to x over 2. So the radius OA of this semicircle equals to x over 2 units in its length, and the radius OD equals to x over 2 units in its length. In the drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point. We define this point, it is the touching point, as point S. So, we have an external notch between the semicircle and the quarter circle. And whenever you have an external notch between two circles or semicircles or quarter circles, you can implement rule 10. So quickly on rule 10, according to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing, we have those two circles and they touch each other externally, this point, point P. So we have an external notch between them, it's point P. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. In our drawing, we have an external notch between the semicircle and the quarter circle. That is to say, they touch each other externally at this point, point S. Therefore, we can implement rule 10. The center of this semicircle is at point O. The center of this quarter circle is at point C. And the straight line that connects the centers together is of course the straight line OC. So this straight line OC must pass through point S, that is their touching point. Again, the straight line OC must pass through point S, that is their touching point. Or OSC is one straight line. Again, OSC is one straight line according to rule 10. So we join points OSC together with straight line, and according to rule 10, the straight line OC must pass through point S. It is very easy to see that the straight line OC indeed passes through point S, that is their touching point. So we shall find out that according to rule 10, OSC is one straight line. If OSC is one straight line, it means that OC equals to OS plus SC. Again, OC equals to OS plus SC. So already know OC equals to OS plus SC. So OC equals to OS. OS is the radius of the semicircle, is equals to x over 2. So here, x over 2 plus SC. SC is radius of this quarter circle is equals to x. So in total we found out that OC equals to x over 2 plus x. X over 2 plus x, that is 1.5x, so 3 over 2 times x units in itself. So if we found out that OC equals to 3 over 2 times x units, and the opposite OC with the right triangle ODC is equals to 3 over 2 times x units in itself. In the next step, I'll copy the right triangle ODC in the new page and we implement the Pythagoras theorem on this right triangle ODC. Here by PT is a proportion for Pythagoras theorem. Side OD equals to x over 2 units in its length. Side DC equals to 5 units in its length. And finally, the length of the opposite OC is 3 over 2 times x units. Firstly, this is the right triangle ODC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ODC, OC squared equals to OD squared plus DC squared. So I'll write it down. OC squared, that is the square of the hypotenuse, equals to OD squared. OD is x over 2, therefore OD squared equals to OD squared plus DC squared. So OC is equals to 3 over 2 times x, therefore OC squared will be equal to 9 over 4 times x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x squared over 4. Plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we found out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation. And we get that 9 quarters x squared plus 1 quarter x squared equals to 8 quarters x squared. X squared over 4 minus x over 4 is 0, of course. So here we're left only with 25. In conclusion, we found out that 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared is equals to 25. So here we divide this equation by 2 and finally get that x squared equals to 25 over 2. So here we take a look at the equation. Finding that x equals to the square root of 25, that is 5, over the square root of 2. So we found out that x equals to 5 over the square root of 2 itself, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area from the line from the line, it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of the quarter circle. So already known, the area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So repeat again. Actually found out that the area of the green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? We know that the area of a rectangle equals to the length of the rectangle times the width. The length is AB, that is 5, the width is BC, that is x, so in total the length times the width is 5x. So we found out that the area of rectangle ABCD equals to 5x minus the area of the semicircle. What is the area of the semicircle? We know that the radius of the semicircle is x over 2, therefore the area must be equal to pi times the radius squared over 2, so it is pi times x over 2 squared divided by 2. So as you know, the area of the semicircle equals to pi times the radius squared, that is x over 2 squared divided by 2. Minus the area of the quarter circle, minus the area of the quarter circle. We know that the radius of this quarter circle is x, therefore the area must be equal to pi x squared over 4. So here, the value of this expression, it is between the brackets, it is equals to the area of the green shape. So what is the value of this expression? It is equals to 5x minus, here we have pi times x squared times x over 2 squared divided by 2. So it is pi divided by 2, and x over 2 squared is x squared over 4. Minus pi x squared over 4. So the area of the green shape equals to 5x minus pi x squared over 2 times 4. 2 times 4 is 8, so in total the value of this expression is equals to minus pi x squared over 8. And here we have also minus pi x squared over 4. So here we multiply both the numerator and the denominator of this expression by 2 in order to common factor with this expression. So after we multiply it by 2, we get that it will be equal to minus 2 pi x squared divided by 8. So there the differential equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8 is equals to minus 3 pi x squared over 8. So we already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Therefore we can substitute x in this expression by 5 over square root of 2, and we substitute x squared in this expression by 25 over 2. We do it now and we get that the area of the green shape in total will be equal to 5 times x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared. X squared is 25 over 2. So in total the area of the green shape equals to 5 times 5 is 25, so the value of this expression will be equal to 25 over square root of 2. Here, in the numerator of this expression, we have minus 3 pi times 25 is minus 75 pi divided by 2 times 8 times 2 is 16. So in total, we found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the value of this expression is equal to 2.95 square units. Repeat again, we should find out that the area of this green shape equals to 2.95 square units. So finish with the second question. The next step of some other lecture, we'll start with the first question, of course. Our mission in this question, the first question, is to find out the area of this semicircle that is located inside quarter circle AOB. So in the drawing we have quarter circle AOB. We know that AO equals to 5, therefore the radius of this quarter circle is equal to 5 units in its length. And again, inside this quarter circle we have this semicircle. Our mission is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. We define the touching point of this semicircle with this quarter circle. This point is point F. And we define the other touching point between the semicircle and the quarter circle. This point is point G. Likewise, we define the point of tendency of tangent OB with this semicircle. This point is point L. We also define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, we define the radius of this semicircle as x. Therefore, CG is the radius of this semicircle that is equal to x, and CF is also the radius of this semicircle that is equal to x. In the next step, we join point C and N together, but join point C and N together by straight line. CL is of course the radius of this semicircle, that is equal to x. Likewise, we join point C and H together by straight line. CH is also the radius of the semicircle, that is equal to x. So here we can implement rule 1 because we have the radius CL that is equal to x. The radius CL is drawn to point L, that is the point of tendency of the BO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent BO will be perpendicular to the radius NO. If BO is perpendicular to NO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius CH that is equal to x. The radius CH is drawn to point H, that is the point of tendency of tangent AO with the semicircle. And whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we can do quadrangle CHOL. Inside quadrangle CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle CHOL we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle plus a square. So we will relate to quadrangle CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the same rule, in the same rectangle CHOL, side CN must be equal to the opposite side OH. But CL equals to x. Therefore OH must be also equal to x. So we can find out that quadrangle CHOL is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square equals to x. In the next step, we join points O and C together by a straight line. By joining points O and C, we can derive an associated triangle, triangle CLO. In the next step, I copied the right and associated triangle, triangle CLO in a new page, and we implemented the Pythagoras theorem on this triangle, triangle CLO. So actually, this is the right and associated triangle, triangle CLO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse in this right triangle CLO is CO, therefore the square of the hypotenuse is CO square, and it must be equal to CL square plus LO square. CO is the missing side, so we leave it as it is, and it is equal to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total, if we found out that CO square equals to x square plus x square, that is 2x square. So CO square equals to 2x square. Here we took out all those equations, and finally found out that the missing hypotenuse CO is equal to the square root of 2 times x units in its length. So this is the hypotenuse CO, that is equal to the square root of 2 times x units in its length. So here we know that point O is the center of the quarter circle. So from this point O, actually here, line segment OC that bisects chord FG. Why line segment OC bisects chord FG? Because of the fact that CF equals to CG. So line segment OC bisects quote FG into 2 halves, each half equals to x. CF equals to x, and CG also equals to x. And whenever you have a line segment that is drawn from the center of the circle and bisect the chord, you can implement rule 7. So please go to rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisect the chord, then that line segment will be also perpendicular to that chord. So in the drawing you have a circle, point O is the center of the circle, so from point O, that is the center of the circle, we have line segment OM that bisect chord AB. That is to say, MA equals to MB. And therefore, according to this rule 7, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say, from this point O, we have line segment OC that bisects chord FG. That is to say, line segment OC divides chord FG into 2 halves, each half equals to x. So all the requirements of rule 7 are satisfied, and therefore we can implement rule 7. According to rule 7, line segment OC will be also perpendicular to FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. You know that the radius of this quarter circle is 5. We join points O and F together by side line. OF is the radius of the quarter circle, therefore it is equals to 5. In the next step, I copied the right angle triangle FCO in a new page, and we implemented the Pythagoras theorem on this right angle triangle FCO. So actually, this is the right angle triangle FCO that I copied from the original drawing. Here by PT is a version from Pythagoras theorem. According to the Pythagoras theorem, in this right triangle FCO, FO squared, that is the square of the hypotenuse, must be equal to FC squared plus CO squared. FO is 5, therefore FO squared is 5 squared, that is 25, and it is equal to FC squared. FC is x, therefore FC squared is x squared plus CO squared. CO is equal to 2 times x, therefore CO squared is 2x squared. So in total, I have found out that 25 equals to x squared plus x squared. X squared plus 2x squared is 3x squared, of course. So we have found out that 25 equals to 3x squared. Here we divided this equation by 3, and finally found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. We know that the radius of this semicircle is x, therefore the area of this semicircle must be equal to pi x squared over 2. So again, the area of the semicircle must be equal to pi x squared over 2. So it is pi over 2 times x squared, and x squared is 25 over 3. So we can substitute x squared in this equation by 25 over 3. We did it, and we found out the area of the semicircle equals to pi over 2 times 25 over 3. So in the numerator of this expression we have 25 pi, and the denominator we have 2 times 3, that is 6. So in total the area of this semicircle equals to either 25 pi over 6 square units, so in terms of numbers the area of this semicircle equals to 13.09 square units. So we finish with the first question. In the next step I presented to you the second question and answered on the second question. In this second question, our mission is to find out the area of this grand shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. Again, our mission is to find out the area of this grand shape. First of all, we define the radius of this quarter circle as x. Therefore, that is to say, BC, that is the radius of this quarter circle, equals to x according to our definition. We know that all the angles inside any rectangle are right angles, and therefore this angle is a right angle. In addition, we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in this length. Likewise, according to the sum rule, in the sum rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. To define the center of this semicircle, this point is point O. So AD is not only one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter AD of this semicircle equals to x. If the diameter is x, the radius must be equal to half of it. So the radius must be equal to x over 2. The radius OA of this semicircle equals to x over 2, and the radius OD of this semicircle equals to x over 2 units in its length. Okay. So here, actually we have an external line between this semicircle and this quarter circle. That is to say, they touch each other externally at this point S. So we find this point that is their touching point as point S. So whenever you have an external line between two circles or semicircles or quarter circles, you can implement rule 10. So I can quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. In the drawing, we have two circles, and they touch each other externally at this point P. So they have an external line between them at point P. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects their centers together is of course the straight line OM. And the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule, rule 10. So we can actually implement rule 10 in our drawing. In our drawing, we have a semblance between the semicircle and the quarter circle. The center of this semicircle is at point O. The center of this quarter circle is at point C. And the straight line that connects their centers together is of course the straight line OC. This straight line OC, according to rule 10, must pass for their touching point, that is point S. Again, the straight line OC must pass for point S, that is their touching point. Or OSC is one straight line. Again, OSC is one straight line. So we join points O and C together by straight line. And according to rule 10, the straight line OC must pass for point S, that is their touching point. As you can see here, we join points O and C together by straight line. You can see that the straight line OC definitely passes for point S, that is their touching point. If OSC is one straight line according to rule 10, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle, that is equals to x over 2, plus SC. SC is the radius of this quarter circle, that is equals to x. So in total, OC equals to x over 2 plus x, that is 1.5x or 3 over 2 times x units in its length. So if you found out that the hypotenuse OC of the right triangle ODC equals to 3 over 2 times x units in its length. In the next step, we copied the right triangle ODC in a new page and we implemented the Pythagoras theorem on this right triangle, triangle ODC. So this is the right triangle ODC that I copied from the original drawing according to the Pythagoras theorem. In this right triangle ODC, OC squared, that is the square of the hypotenuse, must be equal to OD squared plus DC squared. OC is 3 over 2 times x, therefore OC squared is 3 over 2 times x squared, that is 9 over 4 times x squared, and it is equal to OD squared. OD is x over 2, therefore OD squared is x squared over 4, plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So if we found that 9 quarters x squared equals to x squared over 4 plus 25. Here we substituted x squared over 4 for this equation and find out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. X squared over 4 minus x squared over 4 is 0, so I'm left here only with 25. So we found out that 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared is equals to 25. So 2x squared equals to 25. We divided this equation by 2 and find out that x squared equals to 25 over 2. Here we took a root out of this equation and found out that x equals to 5 over square root of 2 instead. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. I repeat again, the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. What is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length AB is 5, the width BC is x, so in total the length times the width is 5x. So the area of rectangle ABCD equals to 5x. Minus the area of this semicircle. What is the area of this semicircle? You know that the radius of this semicircle is x over 2. Therefore the area must be equal to pi times x over 2 squared divided by 2. Again, the area of the semicircle equals to pi times x over 2 squared divided by 2. Minus the area of the quarter circle. What is the area of this quarter circle? We know that the radius of this quarter circle is x. Therefore the area must be equal to pi x squared over 4. So it is minus the area of the quarter circle, that is minus pi x squared over 4. So we know that the value of the expression that is between the brackets here is the area of the green shape. So what is the value of this expression? This expression equals to 5x. Here we have pi times x over 2 squared divided by 2. X over 2 squared is x squared over 4. So in total this expression will be equal to pi x squared over 4 divided by 2 minus pi x squared over 4. So here we have minus pi x squared over 4. So the area of the green shape in total equals to 5x. Here we have the numerator 2 times, in the denominator we have 2 times 4, that is 8. So in total the value of this expression is pi x squared over minus pi x squared over 8. Here minus pi x squared over 8. Here we have pi x squared over 4. So here we multiplied both the numerator and the denominator of this expression by 2 in order to have a common factor of this expression. After multiplied by 2, we should find out that the value of this expression equals to minus 2 pi x squared over 8. So the area of the green shape equals to 5x. Here we have minus pi x squared over 8 minus 2 pi x squared over 8 is minus 3 pi x squared over 8. So in total we should find out that the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2. Therefore we can substitute x in this equation, this expression by 5 over square root of 2, and we can substitute x squared in this expression by 25 over 2. We did it and we found out that 5x equals to 5 and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total we found out the area of the shape equals to 5 times 5 is 25, so in total the value of this expression is 25 over square root of 2 minus 3 pi over 8 times 25 over 2. So in the numerator of this expression we have minus 3 pi over 25, that is minus 75 pi. In the denominator we have 8 times 2, that is 16. So in total the value of this expression is equals to 175 pi over 16. And in total we found out the area of the shape equals to 25 over square root of 2 minus 75 pi over 16 square units. Or in terms of numbers, the value of this expression is 2.95. So in total we found out the area of this green shape equals to 2.95 square units. Okay, thank you very much.